All right, thanks. So this is a moderately ambitious talk, so I apologize in advance for speaking fast. We have quite a bit of material to get through. And first, a few disclaimers. So since I technically still work for the White House, this could be construed as an official White House talk, but this is not. I have to put this disclaimer in front of pretty much every talk I give these days, which is that this is a personal talk. This talk may not reflect the views of the president or the administration. But what I can tell you is that they certainly used to. And these days, I'm told that there's this service called Twitter, which is the source of all official policy. So if you want to know the official, just look it up there. Anyway, so yeah, the war on error. So I'm going to argue that error is bad, that error in code is bad, and that code for software, when it goes wrong, does bad things. Things blow up because things are incorrect, or we get terrible security vulnerabilities that cost billions of dollars. So that's bad. But bad things happen when you get errors in code for people, too. When you get errors in code for people, and by that I mean, of course, in your DNA, in your genome, you get things like terrible genetic disorders, chronic conditions, and things like cancer. So error for code in people is bad as well. And I'm going to argue that we can fix both of them. I'm not going to fix both of them in 40 minutes, but I'm going to argue we can fix both of them. And the unifying theme for how we're going to fix these problems is approximation. We're going to find ways of approximating solutions so that we can find ways of fixing code for both software and for people. So the main idea is on the software side, if I will make the claim that if we could solve the halting problem, it would be a lot easier to solve many issues with software. So if we had some magic function that took a program and mapped it to whether or not it was going to terminate or not on some given input, then this would solve a lot of problems for us. It would be very easy to make software better. Of course, we can't solve it, but we can approximate the solution to the halting problem. If we're allowed to say, I don't know, for whether a program halts or not, then suddenly it actually becomes a very easy problem to solve. We can always say, I don't know. And the same goes for people. So we can take a person or a tumor or something like that, and we can find in their code the source of the problems that drive their disease. If we can find the mutations that are causing a particular disease, then maybe we can use that information to find the perfect treatment for them. This is a new kind of medicine we call precision medicine. So in this case, we're also in some sense building a function that maps a person, or really their data, because it goes well beyond the genome, I will say, and maps that into the right treatment for them. But of course, we can't do this either perfectly. We're going to have to come up with some kind of approximation that gives us sets of possible treatments, or in many cases, a set of scientific experiments to run that will take us closer to knowing what that right treatment is. So that's the idea. So let's do software first. So software's terrible. I think we can all agree on that. And we've reached an era where we have security vulnerabilities that not only have their own logos, but their own product line. So this is not good. And it costs billions of dollars, and that's bad. And pretty much everything is hackable these days, including apparently even restrooms. Did not know that. Until, of course, you actually visit in Japan and realize that toilets are, in fact, quite hackable as well. So it looks like we really need security everywhere these days. Okay, so why is this? Why has things gone so wrong for us in software? Well, there's a number of reasons. I would say, language choice has certainly been one of them. Attitude is perhaps another. But I think what we can do is we can find some solutions, based on these observations. I think what we need to do at the end of the day is engineer software. And what's interesting is we have a field in academia called software engineering, but to argue that we don't really do much real engineering in the classical sense within software engineering. With apologies to all the software engineers, it's really good I'm leaving computer science and PL while I make these statements, I guess. Because maybe my peers wouldn't be so kind next time. So yeah, engineers use prediction. I think that's sort of one of their core tools in the tool chest. That's one of the I think the defining attribute of engineering. So that if you were to do something with the physical world, you have things like Newton's laws that will tell you how physical systems evolve over time, and very precisely over time. So if you know the acceleration and mass, you can go to velocity. From velocity, you can go to distance, and from this, you can actually sort of plot the course of something like a projectile. So that if you're a military engineer, you can very accurately predict what's going to happen if you need to fire something at an enemy ship so that you can be guaranteed it'll actually hit its target. You have that level of resolution when you're an actual engineer as opposed to a software engineer, where it's very difficult to predict the behavior of these systems. And another example of why I think software engineering doesn't really resemble engineering in a classical sense is the way we build bridges. So I remember when I was taking software engineering as an undergraduate, and when I was in the software engineering class, this cartoon flashed into my head, and I thought, oh my God, this is what we're doing. In it, Calvin's asking his dad, how do they know the load limit on bridges? And his dad says, well, they just drive bigger and bigger trucks across the bridges until it breaks. Then they weigh the last truck and they rebuild the bridge. And I'm like, yeah, that's what we're doing. That's like all this test-driven development. That's what we do in software. We just drive trucks across our software till it breaks. But if you're an actual engineer and you want to build a bridge, well, of course, you actually have access again to tools like static and dynamics and tensile strength models, and you can use this to predict the behavior of a bridge under a continuum of circumstances. You can do that if you're a civil engineer, but it's difficult to do the equivalent if you're building software. So, can you predict software? Well, in a nutshell, no, you can't. So Alan Turing, right off the start, says, nope, just forget it. It's the 11th commandment. So we're kind of stuck there. So that's kind of a bummer. Okay. So the way I look at it is, in physics you have black holes. The boundary is beyond which you cannot see. Whereas in computer science, what you have are the loops or the loopholes. These are the horizons beyond which you cannot reason, at least in an strictly automated fashion. Of course, we do reason about them all the time. So what can we do? Well, we could stop using 1970s technology to build our programs. So we could switch away from that towards something at least 90s era and far more sophisticated. Or we could go to an alternate universe altogether, maybe an even better one, where we prove our software correct from the beginning. We could do that too. And that would also be a fine way to go about things in solving this problem. But this doesn't do a whole lot for us in terms of the legacy code that's out there. And there's an awful lot of legacy code that we've got to fix. So I did have at one point a large project called Crash. It was dedicated to sort of the older techniques around this, or these sorts of approaches to solving the software crisis, and that was a lot of fun. But I think there's another way we could go about this. Of course, there's several ways we can do this, but the one that I like to go after is through static analysis. So what I want you to do is imagine the execution of your program as the evolution of a trajectory through some state space over time. You're moving through a sequence of states, and what you want to know is, when you're playing this game, is can you approximate or bound the trajectory of this line in somewhere, the sequence of states, so that you can know for sure that you're avoiding bad regions of the state space. Regions where you're overflowing an integer, or regions where you're overflowing a buffer, where you're doing something bad, or some kind of behavior you want to avoid. You want to know, can you approximate it sufficiently tightly to prove that this program doesn't enter any of these regions? Yeah, in this case, if this is your approximation, no, you haven't done it. It still thinks you might do evil in some sense. It still thinks you might overflow a buffer. So the game is really to come up with ever tighter approximations so that you can provably avoid those regions. And again, as a fully automated fashion as you can possibly do. So that's the game. So how do you play the static analysis game? Well, there's a general methodology out there called abstract interpretation developed by the Cuzots. And what I'm going to tell you about at a very high level is a specific instance of that methodology called abstracting abstract machines. So this first appeared for me and David Van Horn back at ICP 2010. And if you really want to dive deeper into this, what I recommend is the JFP 2012 version of this, which includes Haskell and math side by side for every artifact we build, so that if you're trying to figure out how to do this for the first time, it's all right there really as a tutorial for you. But what's the core idea behind using abstracting abstract machines to approximate program behavior in such a way that we can make predictions about what it will do? Well, the core idea is to take an interpreter, pass it through some process, that's the abstracting abstract machines process, and get an approximator out the other side. So to do this, we're going to deal with small step interpreters. So we're going to need some sort of injection function that will take a program and push you into some state space. Then what we need is some step function that says, okay, if I'm in this state, this is my next state, so that we can just drive execution forward one state at a time. So here's an example of what some of these roles actually look like in practice. So this is for sort of a minimal approximation of the Dalvik virtual machine. And here's what execution looks like if you're doing it concretely. You inject into your state space, and you just step, 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 step forever. Now, if you could just observe all the states you might visit, then you could ask a question like, in any of these states, is there a security vulnerability? Is that a problem? But of course, you can't in practice because this might go on forever. There's no guarantee that when you start running this thing, it's actually going to stop. So what we have to do instead is come up with an approximation of this execution. We need an abstract interpretation. And what that's going to look like is this sort of projection into this finite abstract state space so that once we start running through it, we're guaranteed to stop at some point. At some point, we're going to run out of states to go through. And we'll have some sort of relation that ties together concrete and abstract states. So if we take the original and concrete execution of the program, we're going to make sure that as we evolve in the abstract, we're maintaining some kind of correspondence with the concrete execution all the time. So that no matter what path we might have taken through the concrete execution, it's going to be represented in the abstract execution somewhere. All right. So the first step here, and I've alluded to this already, when you're doing abstracting abstract machines, is to diagnose the problem. Why is it that you can't just use the concrete interpreter to sort of fully explore the state space? And the answer is, I think, readily apparent, is that it might not stop. If you just start taking steps, you might never stop taking steps. You have an infinite state space through which you might traverse. And so there's reasons why it's potentially unbounded. If you look inside one of these states, you're going to have things like, well, depending on what kind of language you're looking at, it might be a frame pointer or an environment. You'll either have an address store or a heap or a stack or continuation or something like that. And three of these components are actually unbounded and driving the unboundedness of the overall state space. So we'll get into that in a second. But these are the three we're going to have to deal with if we want to come up with some sort of approximating interpreter for the language. So we've got this unboundedness in the state space, and we want to get rid of that. We want to crunch it down to some finite space. That's the whole idea behind abstracting abstract machines. So the next step is to abstract. In this case, and for now I really mean finitize. We're going to try to take all these components and give them a finite world to live in. So we'll do this for a specific machine. We're going to do this for the CESK machine. And CSK machine it's a very nice general model that I can fit almost every language I've dealt with so far into. First developed by Fleiss and Friedman back in 1987. And the four components are control, environment, store, and continuation. And so you have four components inside every single machine state. And in the case of a functional language, the C is going to be an expression usually, or sometimes an expression context. The E in this case will be a variable that maps to, it's going to be an environment that maps variables to addresses. So if you want to look up a variable, you first look up its address, and then you look in the store, the S, to find its actual value. So it's a two-stage lookup process now for every variable. And then down the bottom you have a sequence of stack frames for the continuation. There's a number of ways to represent continuations, but this one works just fine for our purposes. What we need to do now is sort of focus on the unboundedness in the state space and somehow crunch it down. So that what's unbounded in this state space really are the sets of addresses, the stack frame, or the stack, and values. So we'll do values first. We'll abstract this down. So values are basic values, in which case we'll just assume that's integers and potentially objects, or actually forget objects. Let's say they're closures. And let's look at how we might crunch down natural number, the integers. So the integers are pretty easy to deal with. If we want to just approximate all the integers, we can do that with what we call the abstraction of signs. So we go from all the integers down to a power set of -0 and positive. And now we can represent not only the integers, but operations of the integers as well. You can take sets of signs and work out what addition and subtraction and multiplication and all that means for them. All right, so now we have an abstraction that works for basic values. So what we need to do next is abstract closures. Well, closures are lambda terms, and for any given program, the set of lambda terms should be finite. Then we have environments. So assuming we can abstract environments, then closures become abstract as well. So now we've got an abstraction for closures, a finite abstraction that is. And next up, values becomes finitized or abstract as well. Once we've got basic values and closures handled, we just handled values at the same time. All right, so that was values. We've now got them living in a finite space. So what's next? Well, we've still got addresses, so we're going to just declare that addresses are now a finite set. All right, so The way we do this is we have some abstraction function, alpha, that takes a concrete address and gives you back an abstract address. So it's just going to choose some representative in this abstract set of addresses. And for our purposes, the abstract set of addresses could even be the singleton set. You could have one abstract address for absolutely everything. It's a terrible way to do it, but it works, from the perspective of soundness. There's probably like 20 years of literature in static analysis that deals with how you carve up how you do this mapping, because this is what determines things like polyvariance and context sensitivity and other interesting properties of the analysis. You get lots of resolution over the speed and the time of the analysis, the speed and space complexity analysis as well when you start playing around with this knob. We're not going to talk about that today, but just to let you know that there's a very principled way of going about doing this mapping. All right, so now we've got addresses abstracted. So the last step, actually before that, we have to realize that as soon as we start sharing addresses, once we have this finite set of addresses, we need to allow multiple values to live at the same address in the store, so the range of the store becomes a power set of values. So now when you look up an individual address, you might get multiple abstract values back, and that's fine. So the last stop is the stack, which is right now a sequence of frames. So what we'll do to handle the stack is we'll refactor it so that it's actually more like a linked list. And then what we'll do is we're going to thread the stack through the store. So we're going to do heap allocated continuations effectively by saying instead of having continuations inside continuations, each continuation will actually have a pointer to the next continuation. And what that means in the context of the larger state space is that we also have to have continuations living at addresses too. So when you allocate a continuation, you might have to allocate a continuation or an address for the continuation beneath it. And when you look up an address in the store, you might get multiple continuations back. So when it comes time to return somewhere, maybe you return to multiple places in your abstract interpreter. That's okay, as long as we're building an approximation of what the real interpreter would do. All right. So we've got addresses that abstract. That takes care of continuations. And now everything in our state space has been abstracted. So we actually have finitized this entire state space. So we have an abstract machine at this point, and we can just run it. We can see where it goes. And what it's going to do is build an over-approximating model of what our original programs might have done. And of course, there's semantics just to show you that this actually does work, or you can actually do this. So here's the concrete semantics for that Dalvik machine. And after pushing it through abstracting abstract machines, you end up with something that looks like this. So I'm not going to go into detail on this, but you can see even visually sometimes that there's a very tight correspondence between the original interpreter and the abstract one. So if you want to know a lot more about this, then I have a talk online where I actually live code an abstract interpreter for a relatively simple language. So if you go here, there's a corresponding blog post with all the code available as well. So if you want to know how to do this in much more detail, go here, watch this video, and again, you'll be stepped all the way through the process of building a concrete interpreter and then building its corresponding abstract interpreter as well, all through this process of abstracting abstract machines. So this question, can we win the game, the static analysis game? Well, in some sense, it'll never really be won. It's a game that's going to go on forever, which is good for people in static analysis. But it turns out, I think, when we focus our efforts on meaningful problems, we can actually start to make a real difference in practice for programs that people care about. So one of the other things I did is I had a project called APAC through DARPA, where what we were trying to do was really anticipate a really terrible idea that's kind of inevitable. So what the military decided they wanted to do was they wanted to give Android phones to everybody and then have an app store where anybody could submit, well, maybe not anybody, but lots of contractors could submit apps, soldiers could download apps, and these would be used on the battlefield with no problem whatsoever. So that was the idea, and they realized at least that this was a bad idea and that there needs to be some kind of measures in place for protecting this app store, and in so doing, protecting the soldiers as well. So, well, what are they worried about? Well, maybe there's a malicious application on there that's actually leaking your device back to some attacker somewhere, so that they know exactly where you are. There's also, I think we can all imagine lots of really bad things that could happen if you open up an app store like this. So the idea for APAC was, well, let's have an auditor. Let's have somebody stand in the middle and do really thorough static analysis to see, as programs come in, if they're good and don't have malicious behavior, that they're approved and that soldiers are allowed to use them. And if they're bad and they try to get in, then we find that and we crush them and we go after the person that tried to submit it. That's the whole idea behind the APAC program, was to build these static analyzers that would be used to audit programs coming into the military app store. So the structure of the program was every 6 months, starting at month 6, we had to go up against red teams that were basically simulating submissions to the app store, some of which were malicious, some of which weren't, and we had to figure out which was which. So how did we do? Well, 6 months into the program, turns out not so well. We got literally everything wrong. It was just like catastrophically bad. And that's when I had to remind my program manager that sometimes there are discrepancies between the vision you include in your research proposal and the deliverable that you get at the end of the day. And he was fortunately very understanding about this, but only for like the first 6 months. He's like, you actually have to solve this problem. So the amazing thing is, over the course of 4 years, we actually continue to do better and better and better in terms of our accuracy in the engagements. And in the process, actually did an awful lot of really good research and static analysis. So there's a number of papers out there that fell out of this project, covering everything from like how to go from finding state to pushdown systems, to analyzing parallel programs, to analyzing programs in parallel, to information flow analysis that we ended up needing to include in order to reasonably start to figure out what was malicious and what was not. Now, it wasn't a totally automated process by the end. There was a human in the loop that was able to use the results of the analysis to make the determination. But in many cases, we got very, very good at highlighting regions where if there were malicious behavior, this is probably where it would be. So this is a really, really fun project. We've got a sequel to this now, where actually what we're doing instead is looking for complexity attacks and things like space attacks. So this can be like an algorithm that's, if you've got some input to the program that takes really, it's very small but takes a long time to run, that's an interesting kind of attack to look for. Or a small input that uses a large amount of memory, or side channels. All 3 of these are in scope now for this sort of follow-on project to APAC. And we're actually starting to see sort of a similar results curve there. We started off terrible, and we're about 1.5 years in, and starting to do better and better now. Even though I think that this sort of class of vulnerabilities we're looking for is actually quite challenging. But we are able to, for programs that people actually care about, programs that people write, we're getting reasonably good at doing automated reasoning for these things. All right, so that's the halting problem. What about people? How do we use approximation to help people? Well, there's a new kind of medicine sort of booting up. It's actually not really a new kind of medicine. It's really a new way of doing medicine. It's all about being data-driven and oftentimes genome-guided. So the genome has got people really excited about this new kind of medicine. Because it happened to be a large new piece of data that is actually pretty informative when it comes to your health, particularly for certain classes of diseases. It can be extremely informative for your health. I would say it doesn't have to be genome-guided. I think if you're using a patient's data to optimize their health, I would say you're doing precision medicine at that point. Because it's really all about delivering the right drug to the right patient at the right time. That is the essence of precision medicine. So I want to talk now about curing cancer. But what I really want to do is clarify that cancer is not one specific disease. Cancer is actually many diseases put together. In fact, cancer is many rare diseases. If you take cancer to the limit, it's likely the case that the same cancer has never occurred twice. If you look at the genetic footprint of cancer, even within the same patient, as I'll explain in just a moment, you get very different cancers from the same originating source. And I'll explain why that is. And so that's why this sort of like, very information-driven approach to curing cancer, I think, is absolutely critical. So what I really want to talk about is how to cure rare diseases. In fact, rare genetic diseases. Because I think a consequence of being able to cure rare diseases quickly is that we will have to be able to cure cancer as well. And if we really want to be able to cure cancer, there's really no way of getting there almost certainly without being able to cure rare diseases too. So curing rare diseases is sort of like the sort of base case for curing cancer. But first, I recognize that this is not a room for biologists, so let me give you a brief background on biology. So in Bio 101, you learn that DNA is char star. You've got 4 letters, A, T, C, and G. And these are represented by nucleotides, and they're bound together in the double helix we call DNA. So the fundamental dogma of biology is that you've got DNA, which has a bunch of genes in it. And these genes are first transcribed into RNA, a very similar alternate alphabet. And then RNA is actually divided up into little triplets called codons, ultimately, at the end of the day. And each triplet is converted into an amino acid through translation. So you get For each gene, for the current understanding of gene that is, which is expanding, I would say right now, you end up with a sequence of amino acids. This sequence of amino acids then undergoes a folding process, and that's because amino acids have these side chains that are, some are electropositive, some are electronegative, some are hydrophobic, some are hydrophilic, some are neither, and it's these interactions between the side chains that ultimately give the final 3D conformation to the protein. There's actually a lot of other stuff that happens after that, including a process called post-translational modification. There's about like 70 different things you can do to a protein after it's been produced that modify it in some way. But then you actually have these agents that now float around inside your cells and do things. They either serve as a structure, sometimes they have enzymatic functions, but they're doing something. They're sort of like the principal agents within your cells. That's how you get proteins. So, and that's what your DNA is encoding, by and large. Your DNA is encoding RNA, and much of your RNA is encoding proteins. There's actually a lot of RNAs now that never translate to proteins, and they do lots of interesting things too, but we're not going to talk about that right now. By and large, if you care about human disease, much of it is really focused within the proteins. And we're learning more and more about what the other regions are doing, but for our purposes, going after the proteins is where the money really is. So many proteins are enzymes, and enzymes are really their functions. They catalyze the transformation of one thing into another thing. So sometimes you get two things coming together to form another thing, or sometimes you take one thing and you split it apart. So that's what many of the proteins are actually doing within your body, which means that the genome has syntax, and in fact it has a semantics. And beyond that, it has an instruction set too. So to give you an understanding of how mutations drive disease, let's actually take a look at this instruction set. So here's a little microgene, and if we split it up into codons, we've got ATG, GCC, and TGA. So ATG is the codon that means begin construction of this protein and insert a methionine. So you always insert a methionine at the beginning of the protein. The next codon, GCC, anybody know what GCC does? No one? Yeah, it's compile a C program. It's amazing that it fits inside the human genome, but no, actually it's just insert an alanine. So all these are just saying insert some amino acid. And the last one, TGA, just means stop, meaning you've hit the end of this protein, eject and fold. So if you put these three things together, this really means this. Begin construction of this protein, insert a methionine, insert an alanine, done. That's the code. Yeah, and it's this when you realize that biologists are just terrible at designing language syntax. So what about mutations? Well, mutations are driving a lot of disease. So if we mutate this sequence, like what if we put an A here? Well, now we've changed the meaning of this program. So instead of this program, instead of inserting an alanine, what you actually have is the insertion of an aspartic acid, which may or may not actually change the function of the protein at all. Some mutations, in fact, many mutations are benign. They really don't do anything, at least the ones that we find in the wild. That's because there's this selective process that gets rid of bad mutations pretty fast. But some destroy function. Some will actually increase function in some way. Some will change function. And it's really, depending on what happens will determine whether or not you end up with some sort of consequence for your health. But rare diseases, by and large, are monogenic in nature. They're driven by a single mutation somewhere in the genome that causes the disease to happen. And so for example, if we have, and I think it's easiest to explain this with the simplest model organism of all, which is the stick figure. And I like model organisms I like stick figures as model organisms because they only have, I think, 6 genes, which is much less complicated than humans, which has around 20,000. So if you have your little stick figure and he somehow has a deficit in gene C, then this is going to cause some change to his phenotype. And so there's something that occurs as a result of the loss of C. Now, what this means is that what we're looking for in terms of a treatment is a way what we're looking for is some sort of treatment that will actually compensate for the loss of C. And if we find that, then hopefully what we've done is reverse the course of that change for this particular patient. Cancer, on the other hand, is multigenic. It's not just one gene going haywire, it's several at the same time. Often starts with just one mutation, but then cascades into many more. Usually one of the first mutations that will happen in cancer is a loss of a tumor suppressor. Once you lose your tumor suppressors, now it's easier for many more mutations to pile on top of that. And some of those will eventually be growth genes that will increase growth rates, and so that's how cancer is sort of this cascading process. To go after cancer, you have to find like multiple treatments for different genes all at the same time. And then because cancer is evolving, you have to keep finding new ones constantly. Cancer is just hard. It's because, again, tumors are evolving. They're undergoing a selective process. So when you're fighting cancer, you're fighting evolution itself inside your own body. It is tough. So if you start off with, with a single cancerous cell, it's going to multiply over time. And at some point, you're going to apply a treatment. And the treatment will work for some of the cells, but some of the cells will actually have, just by luck, in many cases, a mutation that gives them resistance to whatever that treatment was. So you can wipe out large fractions of the cells with a particular treatment, but some survive. Sometimes undetectably many, but sometimes you can see a residual. And then these things keep dividing. But they're carrying with them the genetic memory of how to resist that drug. So as they divide, if you apply the same treatment, it doesn't work. It's resistant now. So that's why cancer is so tricky, for one of the many reasons, I should say. So curing cancer is kind of like curing many monogenic diseases on the fly. Because every time you get a new mutation, you've got to find a new treatment, a new way of addressing the gene now driving or the mutation now driving that particular cancer. So that's hard. Hopefully I've convinced you that monogenic disease is sort of the base case for going after cancer. So can we cure monogenic disease? I think we can, and I think we need an algorithm for doing this in a very systematic process that takes as input a patient and their gene defect, and at the end of the day, gives us out some sort of medication we can give them, or maybe a set of experiments we run to get us closer to that. So I'm not going to step you through the entire algorithm, but I've put a lot of thought on this over the past several years, and I've developed one, and I've actually been applying it in practice to real patients. And this is what it looks like in this flowchart form. But again, it's patient data going in, often genomic data, and it's moving through a process whereby we figure out some drug that's going to counteract the effect of that mutation. That's the whole idea behind this algorithm right here. And it always ends in something like clinical trials, although we're finding ways to get around that too, and gets a treatment to a patient. So the question is, will it work? And the amazing thing is I've had a ridiculous sequence of opportunities to be able to answer this question. I'll tell you it does. What I want to do now is tell you a very personal story about why I even do this. I'm a PL researcher by training. Why am I doing medicine at all now? Well, this is my son, Bertrand, so I'll tell you his story very quickly. And this is the story of what happens when you're told that your child is actually the very first case ever discovered of an ultra-rare genetic disorder. So when Bertrand was born, we didn't know why he had developmental delay, why he had seizures, why he had a movement disorder, and why for some reason he just couldn't cry tears. We didn't know why any of that was happening. And that would have been the case for pretty much forever. It had not been for after about 48 months, a team of scientists at Duke stepping up and saying, we will do the sequencing that it will take to find the source of your son's disease. Because I'd been trying to do this for a couple of years at that point because I really believed it was a genetic disorder. So we actually did sequence my son's genome, but we also sequenced mine and my wife's, looking for any potential de novo mutations as well. And what they found, what they told us, this is 5 years ago, almost to the day, was that he'd inherited 2 mutations in a gene called NGLY1 or NGLY1 that knocked out the function of this gene. So for me, he got a premature stop that basically put a stop instruction right in the middle of this gene that said, eject after you're halfway done. For my wife, he got a deletion of a single base pair that garbled all the instructions that came after that point. And then they said, he's the first and the only patient we have ever seen with this disease. He's in many ways an N of 1. There's no evidence in the literature of this gene ever even causing human disease before, let alone the existence of another patient. So the question is, well, how do you know that this is really the cause of this disease? And this is often the first step in precision or genomic medicine. How do you know that you found the right mutation to treat in the first place? Because there's lots of them. Well, if you're a computer scientist, you might want to lean on something like molecular dynamics, where you take the protein, you take the gene, you look at the consequence of the mutation. First, you fold it, you figure out what it looks like, and then maybe you do some sort of statistical simulation to figure out how it's changed in some way. That maybe you increase function, decrease function, change function. But it turns out you really can't use something like molecular dynamics for this problem because it just doesn't scale. It is an incredibly computationally intensive problem. So we need a workaround. And we got lucky in that we're building the workaround thanks to this guy. So Obama, about 2 years before he left office, announced the launch of the Precision Medicine Initiative. What this is doing is it's collecting 1 million the genomes and health records of 1 million Americans, putting them together in a single database so that we can actually use it sort of like a Rosetta Stone for the human genome. And by this, I mean, if you want to know what a mutation is doing in terms of human health, you can look into this database and say, well, what does it do on average to other people? What is it really doing to people when you find something like this? So we're building a way of sort of jumping straight to the end. And I look at it to a genetic telescope so that we are starting to sift apart what mutations mean into their consequences for human health. So some of these mutations will give you a predisposition to cancer. Some may protect you from cancer. Some will give you a predisposition for heart disease. Some may protect you from heart disease. And over the course of the next few years, we're going to learn about all of these and what they do. All right, but what about my son's mutation? That database doesn't exist now, and it didn't exist then. How do we know that that was really the cause of his disease? Well, to figure this out, I wrote a blog post. And I did some calculations to show that, based on the frequency of pathogenic alleles, there was probably somewhere on the order of 500 patients out there in the world that had this. They just didn't know what they had, and I wanted to find them. So this blog post was designed to do two things. It had to go viral, and it had to rank highly in Google search results. So it's just basic SEO. And this is the blog post that I wrote, and there's actually 5,000 words beneath this, but the picture of Liam Neeson, that's to make it go viral, because the internet's kind of sadly predictable. It's amazing how well this actually worked. I'm pretty sure I could have put a cat picture there too, and bet it would have worked just as well. But the 5,000 words below, that was for search engine optimization. And crazy thing is it actually worked. It did go viral, seen by millions of people in a very short amount of time. It did rank highly in Google search results for all the terms that a patient or a parent of the patient might actually type in if they were trying to find somebody with the same thing. And so almost overnight, literally within weeks of discovering this disease, we went from being the only patient in the world to having patients popping up all over the world. And literally 2 weeks later, we had patients in Turkey. And so what this did for us is it sort of washed away this dark night of uncertainty and replaced it with the sunlight of science and community. And we've been a very united community ever since. I think having this community to draw on to actually go after the disease has been a very powerful thing for us. I won't go into details about what happened in terms of that. If you want, there's an article in Youre about what this process was like, and you can read that some other time if you're interested. In fact, turns out there's patients in Barcelona. So last night I was having dinner with one of these patients, which is just kind of an amazing experience. I think you can go almost anywhere in the world now, and I end up meeting one of these patients, because there's 57 of them that I've discovered in the past 5 years through that blog post. But what about finding a treatment? Well, it turns out, since we understood the root molecular cause of this disease, I could reason about what might be going ultimately wrong and potentially ways to fix it. So the enzyme he's missing is called N-glycanase, and N-glycanase is responsible for deglycosylating misfolded glycoproteins after they've been translated from the insulin into the cytosol. So, there are sentences I never expected to have to say as a parent, and I guarantee you that was one of them. What this means at the end of the day is that he is missing a critical recycling enzyme. So there's a kind of waste depicted here that he can't recycle. And as that waste starts to pile up in a very particular way, it actually starts to sequester certain metabolites. There's certain things that go deficient in him, or I hypothesize would go deficient in him, as a consequence of this missing enzyme. So this little blue square in particular is the thing I thought he was deficient in. It's a rare monosaccharide called N-acetylglucosamine. You wouldn't ordinarily eat it unless you eat the shells and shellfish, but it's not something that's totally necessarily ridiculous to put inside a human body. Even so, once I realized this, what I did is I found out you could buy it on Amazon, so I did. I took a bottle of it myself and didn't die, because in my household I am the FDA, and so I remind folks that I'm not literally the FDA. And then after a serious hospitalization where I sort of weighed the ethics of giving it or not giving it to him, I realized that I could never live with myself if I hadn't tried this, if I didn't know if it worked for him. So I gave it to him, and about 3 days after he was on it, for the first time in his life, or the life of any patient for that matter, he started crying tears. So that was unexpected. And over the course of a few months, his nighttime seizures also subsided and almost disappeared entirely. So that was, I would say, one small tear for Bertrand, but it really became an ocean of science for the disorder as a whole. And I did what any parent would do when they saw their child cry for the first time. I took his tear, I packed it under ice, and I shipped it to a lab in California for analysis. And I literally did that. And when I give this talk to biologists, they say, well, that's great, man. It's wonderful that this works in humans, but does it work in flies? And because biologists are very weird, and they just want to know these things. So we built a fly model of the disease, and sure enough, it actually works there too. So flies have about a 17% survival rate with this disease, but if you give them this compound, they go up to about 80-90% survival. So it works in people, works in flies. That's pretty good, actually. And in general, I think we could automate this process of discovering deficits by realizing that you can represent reactions as term rewriting systems. Well, other people have made this realization. You can represent these reactions, these enzymatic reactions, as essentially term rewriting systems. And there's even programming languages where you can represent or write these things down too. So you can use a language like Kappa to simulate and find these deficiencies for other diseases, just like I did for Angli-1. At this point, I went really from computer science into biology and medicine to do what we call traditional or rational drug development. I got a grant to actually do drug development for this disease and built a worm model of the disorder, a planarian worm model in particular. And planaria are great because if you cut them in half, you actually get 2 planaria. It's like 2 for the price of 1, plus some scissors. The great part about giving them, about this for Angli-1 is that if you give them Angli-1 and you cut them in half, what you get is a worm that's been cut in half. So it disrupts their regenerative capacity. So this gave us the basis for what's called a screen, a genetic screen that looks for a modifier that actually can determine whether or not there's some other gene that gives you an advantage in this disease. So what we did is we started knocking out other genes in addition to Angli-1 to see if any of them could restore the regenerative phenotype, and one of them did. So we found essentially a second gene. So what this means is it's better to be missing 2 genes than 1. So there's a second gene you want to get rid of if you also miss Angli-1, which means we're looking for an inhibitor for that second gene. And to find that inhibitor, we went back towards computer science, because what we did is we started with a bacterial model of that second gene. We tweaked it to look like the human version through a process called homology modeling. And we looked for small molecules that were inverse in shape and charge to the catalytic domain on this target. We looked through about 200,000 molecules altogether. 70 compounds actually showed up in the screen. 14 of them were FDA approved. 1 actually worked in the lab when we checked it to see if the prediction was correct. Because again, this is an approximative process. And that one is Prevacid. So you can buy Prevacid at Costco. And obviously we did. And he's been on it now for about 4 months. And there's already substantial benefits for him in terms of, I think, regaining many of the developmental aspects of his disease. So I've seen him doing things now that I haven't seen him do in 9 years since he was a 1-year-old. In fact, I got a publication on this just a few weeks ago. And the crazy part is whatever else I publish for, I think for the rest of my life, I think this will always be my favorite publication about finding a treatment for my son's disease. So I love Popple, I love PLD, I love all that, but this for me is where it's at now. And the question is, will it work again? And will it scale up? And I got, again, a sequence of extraordinary opportunities to really test this out in practice. So a few years ago, the Harvard Med School asked if I would join the faculty. Of course, I said yes. Then Obama said, come to the White House and help engage in setting up the Precision Medicine Initiative, and I said yes to that too. And then about a year ago, I announced jointly with the president an experiment, essentially, to see if precision medicine would really work in practice. And the experiment was, can we go after 5 diseases in 12 months? Repeating essentially that process that I'd done for my son, but for these other rare diseases. And the crazy thing is, it worked. Over the past 12 months, we actually found treatments for 5 diseases. I won't go into the details of that, but in order to do it, I essentially put together a processor for that algorithm, stitching together a substrate from a number of different entities that would enable me to actually execute paths through it in a fairly efficient way. So these are the 5 entities that joined that initial substrate. And I was actually, I found it was great that I actually go to him right before he left office. So this was 3 days before he left office. I actually got to go back to meet with him and say, look, we actually succeeded on those goals. So precision medicine, I think, is definitely going to be real and really enabled as a consequence of this initiative that you've set up. So it's been fun working at it was fun working at the White House. It's been interesting lately, I will say that much. But it was I think the privilege of my life to be able to work for him and to actually execute this project on behalf of patients everywhere. And in terms of my future, I'm actually kind of leaving PL. This is my last lecture as a computer scientist. So I'm leaving my professorship in computer science on July 1st and picking up a professorship in medicine at UAB, where I'll actually be a professor in internal medicine, which is really strange, and director of the Hugh Call Precision Medicine Institute. So I'm building this thing from scratch, hiring a faculty, and executing this vision of bringing this algorithm to patients everywhere. So I think in conclusion, the war on error is tough, but through mechanisms like approximation, I honestly believe it is ultimately winnable. So thank you. Do we have any time for questions? One question.
Yeah, we could do one question. Anybody?
Okay, so my question is, how do you see the impact of projects like the 1000 Genome Project in UK, for example, regarding precision medicine?
So that's a great question. So in the UK, there is like the UK Biobank. I think that's what you're referring to, where I think they have 250,000 individuals that have volunteered biospecimens and their health records. It's been interesting because it's definitely been cited as a forerunner of the precision medicine initiative, where we're collecting 1 million Americans. It hasn't yielded as much as we'd hoped yet, in part because apparently the electronic health record format for the UK is not entirely unified. So it's been very difficult to pull results from across the entire system. There have been some already. So, for example, a number of genes responsible for influencing height have been pulled out of the UK Biobank. In terms of finding genes that directly, identify human diseases, not as much as we'd hoped so far. And some of the drawbacks of the UK Biobank are being, addressed in both the Precision Medicine Initiative and another program in the US called the Million Veterans Program, so that hopefully we'll have a more a tractable way of getting these answers from that data. So that's a great question. Yep.
Do the last one.
Okay. So whenever I hear talks about how our bodies work, I'm astonished that it all seems like such a Heath Robinson arrangement of things that inhibit this, and it seems astonishingly complicated. And whenever people talk about cancer, you say there's many diseases, it just seems unreasonably complicated. The amazing thing about what you're describing is that you've had some success, right? Whereas everyone else seems to make tiny incremental progress. Do you think that will scale? Do you think this was really going to work on the big scale, or do you think you kind of that'll sort of run into the sand of the complexity of the way our bodies amazingly work at all?
That's a great question. And so I think there are large regions of the genome for which this will scale, where if the thing we need to address is a particular kind of gene. So I'll give you an example. There's a large number of genes called ion channels. These are basically little circuits in the membranes of cells that let ions pass in one direction or another. If the defect driving your disease is one of these, I guarantee you we can do something for you today. We know how to hit these things left and right with drugs. We can make them go up, we can make them go down. So if you've got a genetic epilepsy or a heart condition or a pain disorder driven by one of these channels, for a reasonably low cost, we can find a drug that will work for you. If, however, the gene driving your disease is in some sort of structural gene, like dystrophin and muscular dystrophy, now it gets a bit trickier. Because now what we're having to do is sort of tweak the structure back into its correct form. That's harder to do with drugs. It's not impossible. And we need broader approaches to do something like that. So we are building an arsenal for medicating the genome as we speak. Rare disease is kind of paving the way because patients are very motivated to figure out the technique that works for their gene. But that arsenal is repurposable as we move on to cancer. And so for every, we can't do it for every gene right now, but what we can do for any given gene is say, even if there's no medication available right now, this is the set of experiments I would run if I wanted to know the answer or get closer to it. So sometimes you can't, so what I say in the context of precision medicine, sometimes science is the medicine. The conduct of doing science becomes the kind of medication that you do. And hopefully we can do it fast enough to save your life, but that won't always be the case, which is why we need more science funding in general.
Okay, let's give Matt a big round of applause.
As bad as well. And I'm going to argue that we can fix both of them. I'm not going to fix both of them in 40 minutes, but I'm going to argue we can fix both of them. And the unifying theme for how we're going to fix these problems is approximation. We're going to find ways of approximating solutions so that we can find ways of fixing code for both software and for people. So the main idea is on the software side, if I will make the claim that if we could solve the halting problem, it would be a lot easier to solve many issues with software. So if we had some magic function that took a program and mapped it to whether or not it was going to terminate or not on some given input, then this would solve a lot of problems for us. It would be very easy to make software better. Of course, we can't solve it, but we can approximate the solution to the halting problem. If we're allowed to say, I don't know, for whether a program halts or not, then suddenly it actually becomes a very easy problem to solve. We can always say, I don't know. And the same goes for people. So we can take a person or a tumor or something like that, and we can find in their code the source of the problems that drive their disease. If we can find the mutations that are causing a particular disease, then maybe we can use that information to find the perfect treatment for them. This is a new kind of medicine we call precision medicine. So in this case, we're also in some sense building a function that maps a person, or really their data, because it goes well beyond the genome, I will say, and maps that into the right treatment for them. But of course, we can't do this either perfectly. We're going to have to come up with some kind of approximation that gives us sets of possible treatments, or in many cases, a set of scientific experiments to run that will take us closer to knowing what that right treatment is. So that's the idea. So let's do software first. So software's terrible. I think we can all agree on that. And we've reached an era where we have security vulnerabilities that not only have their own logos, but their own product line. So this is not good. And it costs billions of dollars, and that's bad. And pretty much everything is hackable these days, including apparently even restrooms. Did not know that. Until, of course, you actually visit in Japan and realize that toilets are, in fact, quite hackable as well. So it looks like we really need security everywhere these days. Okay, so why is this? Why has things gone so wrong for us in software? Well, there's a number of reasons. I would say, language choice has certainly been one of them. Attitude is perhaps another. But I think what we can do is we can find some solutions, based on these observations. I think what we need to do at the end of the day is engineer software. And what's interesting is we have a field in academia called software engineering, but to argue that we don't really do much real engineering in the classical sense within software engineering. With apologies to all the software engineers, it's really good I'm leaving computer science and PL while I make these statements, I guess. Because maybe my peers wouldn't be so kind next time. So yeah, engineers use prediction. I think that's sort of one of their core tools in the tool chest. That's one of the I think the defining attribute of engineering. So that if you were to do something with the physical world, you have things like Newton's laws that will tell you how physical systems evolve over time, and very precisely over time. So if you know the acceleration and mass, you can go to velocity. From velocity, you can go to distance, and from this, you can actually sort of plot the course of something like a projectile. So that if you're a military engineer, you can very accurately predict what's going to happen if you need to, fire something at an enemy ship, so that you can be guaranteed it'll actually hit its target. You have that level of resolution when you're an actual engineer, as opposed to a software engineer, where it's very difficult to predict the behavior of these systems. And another example of why I think software engineering doesn't really resemble engineering in a classical sense is the way we build bridges. So I remember when I was taking software engineering as an undergraduate, and when I was in the software engineering class, this cartoon flashed into my head, and I thought, oh my God, this is what we're doing. In it, Calvin's asking his dad, how do they know the load limit on bridges? And his dad says, well, they just drive bigger and bigger trucks across the bridges until it breaks. Then they weigh the last truck and they rebuild the bridge. And I'm like, yeah, that's what we're doing. That's like all this test-driven development. That's what we do in software. We just drive trucks across our software until it breaks. But if you're an actual engineer and you want to build a bridge, well, of course, you actually have access again to tools like static and dynamics and tensile strength models, and you can use this to predict the behavior of a bridge under a continuum of circumstances. You can do that if you're a civil engineer, but it's difficult to do the equivalent if you're building software. So, can you predict software? Well, in a nutshell, no, you can't. So Alan Turing, right off the start, says, nope, just forget it. It's the 11th commandment. So we're kind of stuck there. So that's kind of a bummer. Okay. So the way I look at it is, in physics you have black holes. The boundary is beyond which you cannot see. Whereas in computer science, what you have are the loops or the loopholes. These are the horizons beyond which you cannot reason, at least in an strictly automated fashion. Of course, we do reason about them all the time. So what can we do? Well, we could stop using 1970s technology to build our programs. So we could switch away from that towards something at least 90s era and far more sophisticated. Or we could go to an alternate universe altogether, maybe an even better one, where we prove our software correct from the beginning. We could do right, thanks. So this is a moderately ambitious talk, so I apologize in advance for speaking fast. We have quite a bit of material to get through. And first, a few disclaimers. So since I technically still work for the White House, this could be construed as an official White House talk, but this is not. I have to put this disclaimer in front of pretty much every talk I give these days, which is that this is a personal talk. This talk may not reflect the views of the president or the administration. But what I can tell you is that they certainly used to. And these days, I'm told that there's this service called Twitter, which is the source of all official policy. So if you want to know the official, just look it up there. Anyway, so yeah, the war on error. So I'm going to argue that error is bad, that error in code is bad, and that code for software, when it goes wrong, does bad things. Things blow up because things are incorrect, or we get terrible security vulnerabilities that cost billions of dollars. So that's bad. But bad things happen when you get errors in code for people too. When you get errors in code for people, and by that I mean, of course, in your DNA, in your genome, you get things like terrible genetic disorders, chronic conditions, and things like cancer. So error for code in people